Hello everyone. Today we are looking at an integration technique called the reverse chain rule. This technique is based on your understanding that integration itself is a technique that is an inverse operation of what we call differentiation. So when we are integrating, we are reversing what we have done by differentiating, or vice versa. So if we can go back to notation, let's start with the most basic notation. We said if y is given as x to the power of n, let me just do it where there is space, because the notation of this whole thing is very important. So we said if y is equal to x to the power of n, the rule of differentiation, which can be proved as well using the first principles, it says dy over dx is equal to n x to the power of minus 1. So that's the rule of differentiation. So we've got two functions here that we've created. The first function is this one, which is y is equal to x to the power of n. And the second function is this one, which is dy over dx. So you take your dy over dx as your subject of the formula, and it is derived from the first equation, which is this. So if we want to integrate the second equation, this means we are going to say, with respect, of course, to x, the independent variable, we're going to say dy over dx is equal to the integral of n x n minus 1 dx with respect to x. So if we integrate this function, this is what we find. The rule of integration says we add 1 and divide. So we're going to have n x. If we add 1 here, we get n minus 1 plus 1. Then we divide by n. This simply changes to x to the power of n. And this is just your y, of course, plus c. So what we can see is equation number 2, which was the derivative of equation number 1. If you integrate it, it goes back to equation number 1. Hence, what I've done here is the reverse chain rule. This is the reverse chain rule. You are simply saying if you integrate a derivative of a known function, you should go back to the known function already. So the known functions are the most basic one are these straight line functions. The y is equal to x to the power of n. Those are the known functions. So if we integrate that, we get to that part. You could see that already if you started without having this part, you only have this part here. You could see already that the rule of integration can be modeled based on this function, because you could see that our function just becomes f of x, because I'm taking into the consideration that, okay, let me keep on with it, as our function will simply be x to the power of n minus 1. This is the function. Then we add this part here, then we divide by n. That's the rule. So it refers back to that part. So you should know the form of this derivative, that it goes back to y is equal to x to the power of n. Another one that should be 2 more, actually. We know again the second one that says any function that is of this nature, it is a function that we know that if we integrate this function, we should actually anticipate that it gives us a function that we know already. What am I saying here? Let me say this function came from this part. So let me change this and say dy over dx. So this function dy over dx is equal to 1 over x. Actually came from y is equal to natural log of x. So when we differentiate natural log of x, we get 1 over x. So when we are about to integrate this function, we are doing the reverse of this part. So we know that we should go back to natural log of x plus c. However, the technique to use this reverse technique rule lies in you appreciating these functions, and then lies in you knowing the relationship between the denominator and the numerator as well. We'll get to that part. So that's basically the idea of what are we doing with the reverse chain rule. All right. There will be another one, obviously, that you need to remember as well at some point in time, which is y. I would say the third one, which is if dy over dx is e of x. If you integrate e of x, it should revert back to e of x. So when I have a function of this nature and it's a derivative, I know that if I integrate it, I go there. So basically, you should know all those type of functions that we're dealing with as a technique. All right, let us look at these examples that deals with the reverse chain rule. So the first one, the examples that we're talking about here, are the quotient forms. And when we look at the quotient forms, what comes into our mind is this part. I will explain it again. When we look at the quotient forms, let me just create some space here. It takes us back. I think this will be enough. So when we look at the quotient forms, it takes us back to natural log of x. Let me explain what I mean by that. So let's look at these forms, these type of equations. So if we can just restrict to what we understand already, we said if y is equal to natural log of x, you will find out that the derivative, which I proved in one of my lessons, is 1 over x. And when you look at this quotient itself, there is a relationship between the denominator and the numerator. So the relationship is, if this denominator is f of x, you find out that if I differentiate f of x, which is x here, I get a constant. So there is a relationship. So we are saying whenever you are going to differentiate any quotient that has got this type of relationship that says y, or rather let me say that says dy over dx, let me use this as your subject formula, is f prime of x over f of x. Of course, you can put an x here because a k, because they are constants to adjust here. If ever a function is of this nature, so we instead of calling it y, we rather call it dy over dx, because we know that we can take it back to what we know already, which is natural log of x, as long as it has got this preserved form. If we integrate this, we know we can take it to y is equal to natural log of x. All right, so let us see how this works now. If you look at the first example, if you look at the denominator, I will choose to call it f of x because it's a function in x, and it's x squared plus 1. And if I differentiate this, I'm going to get 2x. So if you look at this quotient, it is structured in that form. It is structured in that form that says dy over dx is equal to 2x over x squared plus 1. It is structured in the form that is that. So what we know is if I integrate this automatically with respect to x, of course, y becomes the natural log of x squared plus 1 plus c by the reverse chain rule. Just like if you integrate 1 over x dx, this becomes natural log of x because the relationship is here, is preserved. That's what we mean by the reverse chain rule. All right, plus c. Next will be b. So we look at b, it's again another quotient, but what we need to establish, is it a quotient of f prime of x over f of x? If we look at the denominator, by now with more practice, you can do this without writing all these things that I'm writing here. This is it. If you differentiate this, you get 2 cos x. So the integral dy over dx, let me call it dy over dx, which is what? Cos x over 3 plus 2 sine x. It is of this form. It doesn't matter there is no 2 here. It doesn't matter there is no 2 here. We will always readjust for that. But what we know is there is a relationship that says f prime of x over f of x. So what are we going to do to put the 2 there, to remove this 2? We are going to divide. Let us put the integral sign, dx here and then dx here. We know this is what we have. But because we're going to have a 2 here, which is that 2 here, we have to remove it. That's why in the formula there is a k. So that the 2, we know that if I do this, this is going to be removed. So the answer is just half natural log of 3 plus 2 sine x by the reverse chain rule. All right, so that's how the reverse chain rule works. Let us look at more examples of the reverse chain rule. Another way of seeing the reverse chain rule is to look at questions at products. We've just done this one. We look at other forms of the functions you're integrating. Some of them are not quotients, but they are actually products. But as they are products, they are again structured in a way that you can determine what is their form. So let us look at this example. This is a product of 3 cos x sine squared x. But one thing that we can see is if you look at, let me call it f of x is equal to sine x. The derivative of f of x, is cos x. So what we can see is the arrangement that is here. The arrangement that is here suits this pattern. This is the pattern I want you to see. It's integral of 3. I called sine of x f of x. So because of that, it would mean this is f prime of x. Of course, 3 is here. Then f of x to the power of 2 dx. So we have this arrangement in this product. And because we have that arrangement, we are expecting that once we differentiate this, once we integrate this, there is a pattern that we can see already. And that pattern says your answer to this function, if this is the one that is preserved, your answer to this function should just be, you can try it, should just be f of x n plus 1. Of course, with a k here, the k you try, you adjust the constant. So the constant is there to be adjusted. That's the question. So because there is a constant 3 here, we'll just put a k here. That will be the answer basically. As long as this product is following this, that will be the answer basically. So you can see that sine of x, of course you put the 2 outside because this is also can be written as the integral of 3 cos x sine x squared dx, like this. So we can see that this is the relationship. Our answer is definitely that. Let us justify it. So what am I saying here? Because of this, let us say, I would say now, because this is the form, I would say my function, my original function, y, should be equal to what? Sine of x. Because sine of x, n plus 1, n is 2 there, so it will be sine of x to the power of 3. The 3. That's my function. And check what will happen if you differentiate this. It's dy over dx. Check what we get. There's a 3 here, then there's cos x here, cos x here, then there's sine squared x. You subtract 1 there. So if you differentiate y is equal to sine to the power of 3, you get this, which is exactly this function. So what it means here, you are actually integrating the derivative of sine to the power of 3. That's what we are doing here. We are actually integrating the derivative of sine to the power of 3. And how do we see that? We simply check if the product meets this criteria. Then that's it. You can see that. And then you can try f of x, n plus 1. Then you adjust the constant. So this function here we are actually integrating is a derivative of y is equal to sine to the power of 3x. So in simple terms, the integral is simply sine cubed x plus c by the reverse chain rule. All right, and let us see if this is consistent again with b. Yeah, it should be, but first of all, you've got to check if it meets the criteria. It's x here, f of x, and then we've got another function which is x squared plus 5 to the power of 3 d of x. So let us check these two products here. The one with the highest power to the power of 3, I'll call it x. I'll call it f of x. So if you look at f of x, it is x squared plus 5. I'm not going to say to the power of 3. I just want this is your f of x. And if you find f prime of x, you get 2x. Even though there is no 2 here, but what is important is this is a linear, same as x. So this is f prime of x. So there is a k that needs to be adjusted. That's what this means. There is a k that needs to be adjusted. So technically we can say if we integrate this, it should be y is equal to f of x to the power of n plus 1. So let us see what is our y with respect to this question. Our y becomes y is equal to x squared plus 5 to the power of 4. That's your y. X squared plus 5 to the power of 4. And if you find dy, let's see if it goes back here. Let's check. It is going to be equal to, you say 4 x squared plus 5. You subtract 3 here. Then you differentiate the inside function. It is 2x. That's how it looks like. And if you want to rearrange it in that order, it gives you 8x x squared plus 5 to the power of 3. Yet here we've got x squared plus 5 to the power of 3, but here we've got 8x x squared plus 5 to the power of 3. What does this tell us? That tells us that we need to divide with 1 over 8. The function y is equal to x squared plus 5 has to be divided with 1 over 8 for it to balance with what we have here. So our answer is simply therefore. But we can see this part, only this part here, is this part here. So this is a derivative of this function with a k. So our answer is just y is 1 over 8 x squared plus 5 to the power of 4 and plus c. That's what we mean integration using the reverse chain rule. Next example. Right, a very good example, which is more of a quotient. Is it a quotient? Yeah. I believe if you integrate 2 plus cot x, you get cos x squared with a minus. So are we in a position? We cannot use the quotient here because of this 3. This is a 3. So we cannot use a quotient here because for the quotient rule to work, it should be strictly f of x, not f of x to the power of n. So we rather actually change this and say this is cosec squared x dot 2 plus cot x to the power of 3. Actually, it's no longer to the power of 3, but to the power of minus 3. Now, when you look at it, you say, this is your f of x, the inside function, and this is our f prime of x. Are they related? Certainly they are, because the derivative of cot x is equal to minus cos x squared. So we know already that they are related to that. So let's use the chain rule. The chain rule tells us that if that's the case, therefore we are going to say our y is just, because we are doing the opposite, the reverse actually, is 2 plus cot x to the power of plus 1 here. So minus 3 plus 1 is minus 2. And you can see that dy over dx will be minus 2 in bracket 2 plus cot x. Then we subtract, we get minus 3. Then we differentiate the inside function 2 plus cot x, which is equal to minus cosec squared, which is equal to minus cosec squared minus cosec squared x. We can now rewrite it in that form. We see that this is the same as saying negative and negative cancels each other. 2 cosec squared x over 2 plus cot x to the power of 3. So that's exactly what we have. The derivative of this function here, the derivative of this function is this function, which is exactly what we have here, except this 2. That's your k. So it is quite straightforward that what needs to be done is to remove the 2. And to remove the 2, we just say y is equal to half of this whole function here, which is 2 plus cot x to the power of minus 2 plus c by the reverse chain rule. So this is quite a very interesting method of integration, even though I don't prefer it, but it is a very interesting method of integration. Another question. Let's look at this example. Again, we can see it is a product. So if it is a product, we might just want to see, is it meeting the form that says f prime of x, let me put a k here, and f of x to the power of n dx. Indeed it does, because if this is your f of x, the derivative of sec is indeed tan. So that is actually met in that fashion. Because 1 over cos, yes, you get that. So we are okay with that part. All right? Now, what does this mean? That means our y, let's check with y, is going to be sec x to the power of 5. Or you can just write it as sec 5x. The notation is the same. There. And when you do, what am I saying? Did I say to the power of? No, actually it has to be to the power of 4. It has to be the power of 4. If we say to the power of 5, we are going to get 5 there. So let's say y, let us differentiate this. Dy over dx is equal to 5 sec x to the power of 4. What's the derivative of sec? The derivative of sec should be sec x tan x. Okay, you can just put it and say cosec x here. By the quotient rule, this is equal to 0 minus, that's your sine, over cos squared x. So it's tan x sec x. So the derivative of the inside function is tan x sec x. So we're going to have the derivative of this function being sec to the power 4 tan x sec x, which is sec to the power 5, which is not what we have there. So because of this is a reciprocal, so we actually have to restrict it to 4 in this case. So that's where the lack of mathematics gets in here. That's why I said I don't prefer it all the time, but it does work. So this changes to 4 and 3. So this changes to, perfect, this changes to 4 here, 4, then this is 3, like that. And then still, this is going to be 4 sec to the power 4x tan x, which is exactly what we have here, tan x sec to the power 4. But there is a 5, and here there is a 4. So what we do, we need to remove the 4 by dividing with 4. That's all. That's our answer. So our final answer becomes y, or the integral is just 1 over 4, then sec x. Okay, there is a 5 there. There is a 5 there, so I should just put 5 here, then sec to the power of 4x plus c. That's the answer that you're looking at right now. So once you've done that, I'm not going to do the other part where you need to just set up the upper boundary and the lower boundary by subtracting and equate that. Then that is done already. That should be actually easy to do once you've got this answer. All right. Let us look at this question again. A very interesting question. It says that's a product as well. As you can see, the product of two functions, which is this function and that function. A quick scan is clear. 3x cubed plus 5x plus 9 derivative is 3x squared plus 10x. So this is arranged perfectly in that order. So what we can do is to just say this is equal to y. Our function is y, x squared, rather it's x cubed plus 5x squared plus 9 to the power of half. Then we have to add another one, which is just x cubed 5x squared plus 9 over 3 over 2. Yeah, and if you differentiate dy over dx, you're going to get 3 over 2 in brackets x cubed plus 5x squared plus 9. You subtract, you just get a half here. You do the inside function derivative, which is 3x squared plus 10x. That's what we want here. And then if we check, do we have what we want? Yes, we have everything what we want except the 3 over 2. So therefore, if that's the case, we need to cancel the 3 over 2. So our answer is just y is equal to 2 over 3 x cubed plus 5x squared plus 9 plus c by the reverse chain rule. All right. Another one is this one, that's the quotient. I'm just doing all the examples that can come into the exam in that form. We can see this is exactly in the form of k f prime of x over f of x dx, because the derivative of cos 3x is 3 sine 3x. Actually, there's a minus there, so they are related in some way. So what we're going to say is this should be, if we take y to be equal to natural log of 1 minus cos 3x, if we take this and if we say dy over dx, it should be equal to 1 over 1 minus cos 3x times the inside function, which is going to be equal to 3 sine 3x, which is basically 3 sine 3x over 1 minus cos 3x. But however, we've got 6 here. So in order to achieve that part with the 6, what we need to do, we need actually to multiply with a 2 to have a 6 there. So we are just going to multiply with a 2 there. And we know this is a derivative. of this function. So the answer is just, in short, y is equal to 2 natural log of 1 minus cos 3x plus c by the reverse chain rule. It is an interesting method of integrating. Looking at the last question, no, not the last one, cot x. I would say try to do this one. You can pause the video and try to do this on your own using the reverse chain rule. However, to do this, appreciate that cot is cos x over sine x, and definitely this meets the criteria f of x, because the derivative of sine is cos, so that's definitely that. And we are expecting that if we say dy over dx, actually, let's say if we just say y is equal to natural log of sine x, what is it that we expect to get? Dy over dx is equal to 1 over sine x times the derivative, which is cos x, which is exactly of what we have in this integral sign, cot x. So the answer here is simply going to be y is equal to natural log of sine x plus c. The last question. So if you're following my videos, I'm going to do the same questions using substitution as well. The last question will be show that tan x is equal to natural log of sec x plus c. So a quick reminder that this is a quotient of this form which also meets this criteria. So as a result, we can just say the integral of tan x should be the same. If we have got a function that said natural log of cos x like this, natural log of cos x like this, dy over dx will read like 1 over cos x times the inside function derivative, which is minus sine x, and this is minus sine x over cos x. So since our function is that, in order for it to meet that criteria because of this k, which is minus 1, it simply means y. Our original function was y minus natural log of cos x plus c. Oh, we don't, yeah, plus c, which is slightly different from what we have there. But what you can do is to check this negative here. If you remove it there, applying the natural log, this is going to be equal to cos minus x plus c. Whereas this is natural log of 1 over cos x plus c, which is basically sec x plus c. Sure. Alright, that's how the reverse chain rule works.